Before we jump into evaluating a series of conceptual models, I wanted to take a minute to explain what a conceptual model is. A conceptual model is a diagram or written description of predicted key relationships between the predicted responses of a population and its stressors. It lays out the environmental pathways and routes of exposure in the context of an assessment. To improve a person's understanding of the subject being modeled by taking complex ideas or processes and trying to simplify them. It also communicates details between people who need to know them, serves as a point of reference, and provides a document or diagram that can be referred to in the future. For model number 1, we will be examining an exposure assessment tool from the EPA. The EPA states that this exposure assessment tool is an approach to quantifying exposure by the measurement or estimation of both the amount of substance contacted and the frequency and duration of the contact by linking these together to the estimate exposure or dose. An exposure scenario is a set of facts and assumptions about how exposure takes place. Indirect estimation of exposure or dose ultimately requires quantitative values to use as inputs to exposure-dose equations. The inputs to these equations are obtained through the development of exposure scenarios. Exposure scenarios rely on data or assumptions about the sources and the releases of stressors of interest, fate and transport mechanisms, and the concentrations of the contaminants. The data needed to bring substance to this model is represented in the form of the equation that follows. Exposure equals concentration times exposure factors. The sum of the concentration defines the overall exposure scenario. The concentration is broken down into the sources and releases being calculated, the transportation method, and the media by which it travels. The exposure factors is the population that's being exposed. Some of the practical uses of this model is to represent exposure dose of toxic waste, chemical spills, trash fires, mercury emissions come from open burning, polycyclic aromatic hydrocarbons, or PATHs. Such pollution can cause lung and neurological diseases and have been linked to heart attacks and some cancers. Some of the limitations of this model lies within the name itself. Most of the figures are estimations that heavily rely on field data that may or may not exist before exposure to have something to compare to after exposure. The simplicity of this model is appealing, but due to the lack of scientific data from all processes, further improvements will probably require that physical, chemical, and biological processes be added to the model and that more detailed consideration be given to spatial and temporal variations. For model number 2, we are examining the EPA's National Ecosystem Assessment Toolkit, or NEAT. This is another conceptual diagram that helps depict how some pollutants flow through an ecosystem and may bioaccumulate in living tissues and thus be transferred across the wide spectrum of animal, plant, and human life. NEAT is designed to be a user-friendly and interactive web-based software application with the capability to conduct 3 main types of analysis on the national level: HAT proximity, air pollutants, and track air pollution trends. NEAT will allow users to examine current data, assess current conditions, assess vulnerability, examine future data, and assess future conditions. The entire suite of tools will be flexible and allow users to conduct the report analysis at national, state, and EPA regional scales. The HAT portion of this toolkit allows users to easily identify facilities and natural resources targets based on very specific criteria. If future research efforts establish thresholds For particular pollutants and ecosystems, the tool can be refined to identify ecosystems exposed to air concentrations above a particular threshold value. Some of these assumptions that the tool makes is to identify critical ecosystems in reporting units that are hotspots of air pollution via deposition, sedimentation, and ambient concentrations. These hotspots will be areas with high values for ambient deposition, sediment, and tissue data. While the conceptual model is easy enough to interpret, the actual data behind it is quite complex. There are numerous variables to take into account for in furthering development of this model. Until the pre-existing data sets have been completed to have a clear and decisive reference point of existing ecosystems, the risk of error in determining if a facility is in violation is enormous. Some of the data, this is a conceptual diagram of vapor intrusions into overlying buildings. This model itself is intended to be intuitive and simple. This model implements the Johnson and Integer simplified model to evaluate pathways into buildings, but includes a number of enhancements that are facilitated by web implementation, temperature dependence of Henry's law of constants, automatic sensitivity analysis of certain parameters. The J&E model was based on a number of simplifying assumptions: homogeneity, diffusion only through surface, and uncontaminated capillary. Some of the data that's put into this model is listed below. This name, there's site name, sample concentration, type of contaminant, temperature of soil and groundwater. From these recorded data, you can determine cancer risk levels and hazard quotients that are presented in the computed indoor air concentrations. Vapor intrusion. Some of the limitations of this model are conditional, such as the presence and suspected presence of naples, heterogeneous geology, fractured media, karst and micropores, site where significant lateral flow of vapors may occur, very shallow groundwater, very small building air exchange, buildings with crawl spaces and earthen floors, contaminated groundwater sites with large fluctuations in water table evaluations, sites with time varying flow rates,